So here we are given this ordinary differential equation, and for this ordinary differential equation we need to find its Green's function. So for that purpose, first of all we consider its corresponding homogeneous ordinary differential equation, which is easily obtained only by putting right hand side equal to 0. You can write it to this is the corresponding homogeneous ordinary differential equation for this given equation, and now its solution is simply where k1 and k2 are the arbitrary constants. Now using this solution corresponding to this equation, we can find the Green's function for this given ODE. Now we take Green's function as here the given interval 0 to 1 has been broken down into two parts, one going from 0 to x dash and the other one goes from x dash to 1. So first we take it as ax plus b, where a and b are any two constants which are actually the functions of x dash. The same way we have taken c and d, which are constant in x but are the functions of x dash. Now we only need to evaluate these a, b, c and d constants, or which are the functions of x dash. For this, since the given operator is a Sturm-Liouville operator, therefore, and also we take this first part as g1 and this second part as g2. Therefore when x equals x dash, then which says that at x equals x dash in the interval which is given in this problem to be 0 to 1, the Green's function g is continuous. So using this we can write, for we have taken x equals x dash, therefore we replace x by x dash. So we have this first equation. Also the second condition which is imposed on Green's function is which in this case where these two dash symbols represent the first order derivatives of g1 and g2, and this is at so at x equals x dash, the difference between the first order derivatives of g1 and g2 is equal to -1 for this problem. And this is simply now this is our second relation, and also the third relation tells us that the boundary conditions which are given with the given ordinary differential equation are also satisfied by these two parts of the Green's function, that is g1 and g2, but g1 will be satisfied at the first boundary value condition, that is at 0, and the g2 part will be satisfied at the second point, which is 1. Therefore we have at x equals 0, since this is the first boundary condition, and when we use this in the in g1, then we obtain simply now for g2 so now we have also obtained this as our third relation. Now we use relation number 2, relation number 3, and the value of b, which equals 0, into relation number 1, and relation number 1 was a x dash plus b equals c x dash plus d. So from relation number 2 we know that a equals c minus 1 x dash b is obtained to be 0 already, and c is equal to we just put c as it is, and d is minus c. So now we can write it to c x dash minus x dash equals c x dash minus c. On solving it, c equals x dash. So and then this simply implies d equals minus x dash, and a, which was equal to c minus 1, is now x dash minus 1, and b is already obtained to be 0. Therefore we have now obtained our required Green's function, which is g of x comma x dash equals, so the first part was ax plus b, therefore it is x dash minus 1 x plus 0 when 0 less than x dash less than 1, and the second part is x dash x, which was cx plus d, minus x dash when 0 less than x dash less than x less than 1, or So this is the required Green's function, and in the given problem, option number 4 is true.